Well, welcome to lecture 9. We'll be covering the Constitutive Law. And so to discuss this, I want to remind what we covered so far. We looked at the concept of stress, and stresses are those internal quantities that react external quantities. While when we look at kinematics, the strain, we're looking at how the structure deforms, and we discovered how the strain can be decomposed, the deformations can be decomposed into translation, rotation, and stretching and distortion. And so we covered that, and we made good progress in understanding that. But the next question is, what is next? And that's where we want to go. So let's consider a body of material B. And this body of material B, is subject to body force BI, traction loads TI, and acceleration AI, and it is reacted by the stresses at this point, which at this point, the stresses are sigma ij. And what we learned is that the system is in equilibrium on a volume element in the undeformed body. And even though the stresses in the undeformed body vanish for this natural state. And so I could state then that sigma ij, comma j plus bi equals rho ai, and if there's no accelerations, we can say this is equal to 0, and this in the volume V. And furthermore, what we want to do next is to consider this body of material, and I'm going to consider an infinitesimal change in the deflection of the particle, and I'm going to assume it changed an amount delta. In other words, say that I have a body of material, and I say that the body of material, if it's fixed, say it's fixed, the body of material is fixed here, I'm going to state that the body is going to change shape to a different shape. And I'm going to say that every point in the body moved an amount. So if we call UI, the U vector deflections, displacements at every point, I'm going to state that every point is getting moved now. Like this point could have moved to this point is moving to that point. So every point in the body is moving some amount, and we're going to consider that change to be infinitesimal and virtual. So it's a fake change. So we'll consider then an infinitesimal change in the displacement of the particle originally at coordinates xj. So in other words, this particle here moved to this point here. So P moved to P prime. And that's what I'm looking at here. And we're going to say that that infinitesimal change in displacement, which is virtual, that change in deflection will denote as del U I xj at that location in place. So we're calling this function then a virtual displacement function. Again, we're considering we know that the body is in equilibrium in the undeformed state, even though the stresses in the undeformed body vanish for this natural state by this equation. Every body in this equilibrium has to satisfy the condition. So if we consider an infinitesimal change of the deflection of this particle originally at this point P, then we can consider a virtual change in deflection to point P prime. So since we've defined a particle coordinate xj on the form body, we will then consider an incremental work of stresses following that particle. And we will be following that. Now, I want you to remember what this really means. This means I'm holding xj fixed. I'm holding this fixed while changing this function u. If you recall, we talked about having, and we can just take the situation of a beam so it's more clear. Since you've seen that example before, I have a beam of material, and if the solution, if the real solution to this problem is a cantilever beam with load P, if the deflections of this body are given by some formula, and this was the exact solution to the problem, and let's call this U3, meaning the deflection going downwards is U3, U3 of X. So that's a real solution. And I were to consider then a virtual solution to the problem, so I'm looking at this instead now, then remember what this means. The del U3 X, and this is X1, if this is X1 this way, then del U3 X1 corresponds to change in height, deflection, between the virtual solution, which is in red, U3 tilde of X1. So that's the change in height, keeping X1 fixed. Very similar in a 3D body, we keep X fixed, but then U is being changed from the real solution to the virtual solution. And so then I can consider the actual, the virtual work done by this change in deflection, which is virtual. And so if you remember from physics, if I were to have a block of material and I moved it some amount F by a force F and it moved an amount D, say, just move that way, amount D, the work done is F times D. Very similarly here, what we're considering then is what is the virtual work done, because the work done is not real. If the change in displacements are virtual, then the virtual displacements cause a virtual work done. So the incremental work done due to the forces acting on the body are really given by del W, and I can now look at this. So this the triple integral of the volume, and they have the body force BI, which is that force is moving through the virtual deflections. So that's why I'm going to write del UI. Okay, and del UI dV, because the body forces act over the volume, if you recall, plus the double integral of where distractions which are acting on the surface. And I'll point to that with this here. You can see distractions are acting on the surface. Let's call that surface A. And then I'll call this Ti, whose normal is acting on a surface whose normal is N. And that's moving through del UI. That's how I get the virtual work done due to the tractions and the body forces. There's also accelerations, but I will make it 0 for now. But clearly, the virtual work done is the virtual deflections acting times the body force, and then the virtual deflection times the tractions. Okay, and then what I'll do next, I'll use Cauchy's relationship to continue moving forward here. So I have del W equals triple integral volume BI del UI dV plus double integral on the surface of interest where, and I'll call this S1, where the tractions are being applied. And then I get sigma ij and j when I use Cauchy's relationship. And so now I have del ui ds. And so now I can use Gauss theorem to convert this into volume integral. And when I do that, I get the triple integral volume bi del ui dv. And I've shown you many times how to do this. And it's quite straightforward. So now this surface integral becomes a volume integral. And I basically have sigma ij del ui comma j dv. So now it's over the volume. And so remember that you can integrate by parts to go from here to here. And I've shown you how to do that. I'll do it here at the very top so you can see what's going on. So triple integral, and I'll do it here in this little corner. So I have the triple integral sigma ij del ui comma j dv, but I'm gonna make this, I'm gonna try to integrate that apart. So this multiplied by 1, so I'll put the 1 on the left hand side, sigma ij del ui comma j on the right hand side, integral apart, so 1 comma j sigma ij del ui, and then plus, and j is j is what was moved here, minus, and then now this is 0, so this doesn't go back into the volume, so this now becomes, this integral here becomes just the cross term, which is boundary term. So this is how we've shown you how to integrate parts and clearly use sigma j and j del ui. So I've shown you how this can be equal to this, and that's what you see there. Now I can expand this comma j and I can apply it to this term and that term very simply, and I'll do that in the next page. So I'll take the comma j and use product rule to move it through, and I'll combine the volume terms into one. So I get del w equals the triple integral bi plus, and that's because I have the bi from here, and I forgot the del ui, so let's put that in there. And then I have plus sigma ij comma j del, and then I have this term. I apologize. So you're looking at this term right here. Del, we're looking at this term right here. So that's sigma j comma j times del ui plus sigma I j del ui comma j, because I'm transferring the comma j over each of the terms, times dv. And then now what I want you to notice is that this factors out. This del ui factors out. And so then I have the bi plus sigma ij comma j times del ui plus sigma ij del ui comma j dv. What I notice now, this dv is over the deformed volume and on the deformed state. And what I notice here is that this is 0 because the body is in equilibrium. I already told you that from this relationship. We know that from this relationship. We've shown that before, that the body is in equilibrium, and so that term will be 0. And so what is very interesting is that the virtual work done by those external forces, we're able to relate them to something going on inside the body. Notice how we started with the incremental work done by external laws, BI and TI. And then as we walk it through and use Gauss theorem, we end up saying that the virtual work done is actually also related to the stresses moving through the gradients of the deflections. which is very interesting that we're able to take an external quantity, which is internal virtual work, the external virtual work done, or the work done by the external loads, and we're able to determine that something's going on that's relating the stress with something going on with the gradient of the deflection. Very interesting finding. And the next thing I want to do, we'll continue then with expanding this term. I want to now study that term carefully. And what I want to do is I want to integrate, I want to expand that term to sigma ij del. And I want to do a little trick. And I'm going to call this 1/2 the derivative of ui respect to xj plus the derivative of uj respect to xi. And then I'm going to add 1/2 derivative of ui respect to xj minus the derivative of uj respect to xi. And what I notice here is that this term, this equivalent to what I got here is the same thing. Okay, why is that? When I look at this term adds up and this term cancels out. So in reality, it's the same thing as what I have written here. The next thing I notice is that this right here is actually epsilon ij. We cover that for infinitesimal changes in deflections. So that's epsilon ij. And this term right here is the rotation tensor omega ij. We covered that before. And so now I have, this is equal to the triple integral of sigma ij del epsilon ij plus sigma ij del omega ij. And I want you to remember how we have talked about that omega ij is a skew symmetric tensor, while sigma ij is a symmetric tensor. So a symmetric tensor times a skew symmetric tensor will give you 0, and you can prove it yourself. And you're left now with something even more interesting. The triple integral is sigma ij times del epsilon ij dv. And what this is telling us is something very powerful. We started with the external work done due to these fake changes in deflections from the undeformed state to the deformed state. And then we walked it through some Cauchy's relationship to convert into volume integral. Then we applied Gauss theorem. And then after that, we end up finding that when I relate this external work done, virtual work done, we get that is also related somehow to the internal stresses, which are reacting external loads, moving now through the virtual strains. And so these are clearly energetically conjugate. They're conjugate to each other, energetically conjugate, energetically conjugate, and they belong to each other, which means there must be a way to relate sigma ij to epsilon ij. And so that is the subject of today's lecture, is to relate sigma ij to epsilon ij, because they must be related, and they're related through the constitutive law, which is a material, you can determine that through material measurements. So let's examine the virtual work. The work done by these virtual displacements is virtual, it's not real. And what we demonstrated in this particular derivation is that the stress, the Cauchy stress, this right here is called the Cauchy stress, is energetically conjugate and is married to this infinitesimal strain. But this integral is performed over the deformed body. And that integral, because the body is deforming, as it's deforming, it will be very difficult to perform this integral. So typically what one approach to do this is to go back to the undeformed body and then perform the calculations there. Now you may ask me, are these calculations valid for large deformation? The answer is yes. While the strain looks like that these strains are the infinitesimal ones, Yes, but the derivatives here, xj and xi, these ones are taken with respect to the deformed configuration. So let's call small x the deformed configuration, and I'll use large X for the undeformed configuration. So what I want to do, and the reason this works for large deformations is that as the body deforms, since these derivatives are taken with respect to the deformed configuration, then it is going to account for all the large rotations and all the things that will happen when the body deforms, stretches, and translates. So as a consequence, what we're going to do now is we're going to try to convert all this into the undeformed configuration, because there we can perhaps perform this calculation a little bit simpler. Another thing I want to point out, notice how the stress, this is the Cauchy stress. This is stress acting on the deformed body, while the strain here is a strain when you're calculating the gradients relative to the deformed body. Look at this d volume. This d volume, this differential volume, is taken on the volume element that has been deformed. So we need to really convert all that to a situation where everything's undeformed. So let's start with that derivation. It's going to take some thought. So I really will appreciate if you work it yourself so you can see how this works out for yourself. So you need to derive this at home, make yourself comfortable that you understand this material. Again, we want to look at how to determine what are the energetically conjugate quantities on the undeformed body. So to do that, we're going to start with a gradient tensor. So the deformation gradient tensor. I apologize for that. Let me see if I can get the pen going here for a second. And I hope you're really engaged with me, that your pen is with you, with me, and that we can walk together to success. So here we have the deformation gradient Fij, and I'm going to use index notation to do this. And remember that the deformation gradient is the derivative of the coordinates of the deformed body respect to the undeformed body. So that's the first step. I want to get there doing this. The second step is that this is equal, if you recall, xi is ui plus xi. So the deformation, the displacement plus the coordinate xi. So then partial against xj. And what I'm going to do now, I'm going to take that derivative. So that derivative is partial of ui respect to xj plus del ij. And so that's a good start. And we've already made progress. So the next step is to notice what I want to do, and I want to show you where we were. So this is what we had earlier, right here. And what I want to do, I want to get to this state. I want to convert this del epsilon ij to the green Lagrange strain tensor, because that was defined on the undeformed body of material. So to get there, very slowly, I need to start looking at the procedure to get in there. So to do that, I need to take the first variation of Fij. And when I do that, then I have to take the derivative of Fij respect to, and I'm going to change the variables. So I'm not using I and j, but I'll use the derivative respect to ua comma b, because when I look at Fij, it only depends on derivatives. So then I'll take that derivative instead, del u a comma b. And here I'm using comma, that derivative is taken respect to the undeformed configuration. And I'm changing the notation a little bit because it will be easier for us moving forward. So continuing on, so x here is the undeformed configuration. And the small x is the deformed configuration. Very good. So we're getting there. So now when I look at that derivative, we only have this derivative respect to this one right here. And that's all that is. And I apologize for that. This derivative here, we want to take this derivative here. So all we have to do then is to proceed forward with that derivation. So then we have del AI, and then we have del JB. And you can see that because this right here, if I define this quantity, then I can call this UI, comma J. Now earlier I was using EI, comma J respect to the deformed configuration. So I want you to be careful here. I've changed the convention a little bit just so that we can move forward a little bit quicker. So the derivative of this is going to give you that clearly. And then you have del U, okay, U, A, comma, B. So that's good progress right there. And the next thing I want to do is to notice that this A and this B repeats, so it collapses into del U, I, comma, J. Now the problem is that this del here that I'm looking at, that derivative here but remember that I want to go back to this strain, and this strain is defined on the deformed configuration. So what I want to do then is convert that to that. So to do that, I'll take the derivative with respect to small. Now I'm going to do small xm, and I'm going to expand on xm. It turned off. So I apologize for that. I apologize for that. It looks like the computer turned off, but it's okay. We'll continue forward. Nothing's going to stop me from finishing this lecture. You guys will have fun regardless. So the small derivative of xm respect to large xj. And so I'm expanding that. The reason I need this in this notation, I need it with small xm is because I want to be able to replace this strain here, which is defined in the on the deformed configuration. So now that I have that derivative, notice how this is again fmj. Very nice. And now I can isolate this apart. So I have fmj inverse del fij, and that's equal to, I mean, that's one way to look at it. I'm going to leave it like that, if that's okay with you guys. I'm going to leave it like this. This is the equation we're going to use later, and hopefully we can get there. Okay, so the second step then is to recognize, second step is to look at the following. We want to look at the derivation of the green Lagrange strain. The green Lagrange strain was defined as E, B, 1/2. And now I'm going to use the deformation gradient to derive that. So we'll continue then with EAB, which is a green Lagrange strain. So start with a green Lagrange strain. And my goal is to relate E, the green Lagrange strain, with small strain epsilon. And this is a relative to the undeformed body, this is relative to the deformed body. So I'm going to use the deformation gradient to make that happen. So that's 1/2 F M A F M B minus del AB. And notice how I have M here because that's F transpose. If you remember, this is the green Lagrange strain can be calculated as follows. 1/2 F transpose F minus the identity matrix. So that's what we had before. And so I'm just writing this in index notation because when you write things in index notation, you can do a lot more. So now let's take the first variation of this, and the first variation of EAB then becomes the derivative of EAB respect to the gradient, deformation gradient. And I'm going to use a different variable here. I have not used M and N anywhere here. I used it here, so I should probably use P and Q, which has not been used. So I want to basically use different variables that have not been used. PQ, And so, and there's a variation. This is times the variation of FPQ. So I'm going to expand on that. My goal again is try to figure out a way of relating these two quantities here. The green Lagrange strain and infinitesimal strains. Infinitesimal strains are defined on the form configuration. The green Lagrange strain is defined in the deformed configuration. When you're modeling biological tissues or large deformations like polymer behaviors, you definitely want to be working with large deformations. That's typically what is done. And so then, and you may have seen in some of the problems that in the latest problem that we solved, it was the heart, and we're trying to model the heart with large deformations. And so that's why I had you guys look at green Lagrange strain, not at the infinitesimal strain, because you need to really understand these large deformations really well to be able to model bodies of materials that exhibit large deformation, such as tissue behavior and membranes. So here I have to expand on this, just reminding you why I'm giving motivation, because some of you may not understand why we're doing it. And so I really want you to pay attention to what's going on here. So this 1/2 times the derivative of this quantity respect to FPQ, that should be relatively easy. You've seen it done. We have to use the Kronecker delta. So you get del MP, del AQ, and all I've done is taken this derivative right there. So they have times FMB, okay? And then we have the product rule, which is what we're using, plus FMA, Kronecker delta MP, and Kronecker delta again, BQ. And so if you're falling behind on index notation, it's important that you review one of my first lectures, because all these letters makes it very confusing, but I don't want you to get confused. I want you to remember that we're basically working with arrays and matrices, but when you write things in index notation, it makes it easier to understand what is going on with the different quantities. Then finally, I have this Kronecker delta AB goes away because there's no F there. So then I just get del FPQ. And so now all I have to do is collapse anywhere I can. Give a second here. So this is very easy. These P and Q, PQ, and PQ here collapse. And this P and this Q collapse. So what you're going to get then is 1/2. And then I'll get FMB del, and then I'll have MA. Sorry, not del MA, but collapse with the deformation gradient del FMA. Okay, plus then I have FMA, and then del, and then again FMB. So all I've done is multiply this through and apply the Kronecker delta as necessary. So this is what we have right now at the bottom right. We're able to find the first variation of this there. And what I'll do, I can substitute this now. I know what that is relative to this quantity here. And so we can do that now very simply. So let's write this in the next page. Del PAB, that's equal. And so then I'll just write down 1/2 FMB del, sorry about that. Very good. So we got that done. And just a second. Right, so we got that done. And now we have to substitute what del Fij is. So we found that del Fij is equal to, from the expression in the previous page, we have this expression there. So that's FMJ times the del of U I respect to small xm. Okay, that's what I have. So I can now substitute it here. So I have 1/2 FMB, and I'll try to use these variables to do that. Okay. The only problem is I use M here. I use M there. And perhaps it would have been better if I use a different variable. So if you don't mind, I'm going to switch this to N. This M's to N. And that's going to force you to go through this again on your own. But I think it's useful to switch it because I already use M. And I don't want to confuse the problem more. N, 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 N. And the next page, and then all these are N's. N, N. And again, N is repeated, so we want to be careful. And then here again, I'll use N just so that we're careful. And since I use M already over here, that's repeated index. So N, 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 N. And so the del of N, NA, what I'm going to do, I'm going to use this formula here to substitute it. So del FNA. So let's start with that. So that's F. So I'm substituting this for that. So that's F. And then in that parenthesis, what we want to put is that second index there, A. So that's A. And this index is repeated. So let's use that M again. That's fine. We can use that. Del derivative of U. And then the I instead of I is N. Respect to small xm. So far, so good. So far, so good. So I've replaced this with this, and I changed indices to be consistent to the formula that I have, plus F and A. And now again, substitute this for whatever I have. So that's del. And notice how, again, I have to, and it's not del, I'm sorry about that. That's F. And then the index that I need there is B here, and I can use M again, that's fine. And then del partial of U, but now is N again, respect to X M. Okay. Now notice how I can factor F and B out. Let's factor F and B out. So you get this. So notice how M is an index that's repeated, N is an index that's repeated. So what we're going to do, we're going to switch the indices, if that's okay with you. Think about it at home. Then if I do that, I get F and B, F and A. But now I have del of derivative of U M respect to X N plus F and A, F and B, del derivative U N respect to small xm. Remember, small xm is small x is the deformed configuration. And so now factor, notice how you can factor these out. So that's 1/2 FMB, FNA. And now we have that this is 1/2 del partial UM respect to XN plus 1/2 del partial UN respect to XN. And notice how this is just del epsilon MN. And isn't that awesome that we're able to relate the green Lagrange strain with the infinitesimal strain in that manner? And so now I have just 1/2. So the 1/2 goes away because I put the 1/2 inside the parentheses. And so now I'm left with FMB, FNA, del epsilon MN. And so now I can solve for del epsilon MN. So I get this, F inverse MB, F inverse NA, del EAB. So now we're able to write the infinitesimal strain tensor relative to the deformed, the undeformed configuration green Lagrange strain. The next step in the derivation is that the D volume has to be written in the undeformed configuration. So that's basically the determinant of F respect to dV naught. Sorry about that. And let's call this J or Jacobian. And determinant F is basically, and I should have written it this way, I apologize, is also like that. The determinant of the deformation gradient is J, so that's dV naught times dV naught. And so now we have all the ingredients and all the pieces to bring everything together. So we'll go to the next page then and kind of bring everything together. The internal virtual work was shown to be the integral over the volume sigma ij del epsilon ij dV. And I want to write this on the undeformed configuration. So that's the integral of V. And now what I'm going to do, I'm going to switch the variable so that I can match it with what I have in the previous page. I can use those indices directly. So this is the same as that. It doesn't change. And then I'll now substitute all the elements of the previous page. So sigma AB, I'll leave it alone. And then del epsilon AB, I have found it fully. That's, in fact, I should just use MN. I apologize. MN, because that's what I used in the previous page, not AB. Let me do that. And now I can just, it's a plug and play now. So I can plug in del epsilon MN from the previous page. I apologize. Okay, so F inverse and F inverse MB NA, and then del EAB. And now I have the deformation gradient, the determinant of that, which is J, and then dV naught. And notice now how the integral is over the undeformed volume, which is very convenient. You can do the calculations there now. So now I'm going to rearrange terms in a way. So I'll bring the J ahead, and I'll write it like this. Just a second. So continuing, I can just arrange all the terms. And so I'll do that. MB del EAB F inverse, and then I have NA, and then I have dV naught. So that is how I found the relationship from the deformed configuration to the undeformed configuration. And so now what I can do, I can figure out And why don't pause the video and see if the mistake, you can find the mistake I made. So you can see here that right now, M and N are free indices, and that should not be happening. So clearly I forgot to write down, and it's okay because we're all humans and this is not easy. So sigma Mn is what I'm missing here. Very good. So we made progress, really good stuff. And now we can identify the quantity we have, which is the green Lagrange strain. And this is really equal to the integral V naught. And you can now arrange terms even more. So J sigma Mn Fm inverse B F inverse Na del EAB dV naught. And I'm going to call this the second Euler-Kirchhoff, I apologize. Yeah, so that's PK2, second Euler-Kirchhoff stress. Just a second. Make sure we're spelling this correctly, so I apologize. So we have Kirchhoff. And that stress is SAB. That's how we write that. So the second Euler-Kirchhoff stress is energetically conjugate to the green Lagrange strain and is defined on the undeformed configuration. And then to write that in matrix format, so you can see this in matrix format, is basically the stress. In some books is going to have it with big S, but some books may have it as couches. It's going to look like couches, but not really. It's going to have a PK2 on top. And if you write it in matrix format, it looks very simple. It's J, and then you have F inverse times the Cauchy stress times F inverse transpose. Let me make sure I write this in an easy way for you to follow. So this is the formula for second Euler-Kirchhoff stress, and that's energetically conjugate to the green Lagrange strain. And so again, both of these formulas are for finite deformation. It's just that one is defined in the deformed configuration, and this one is defined in the undeformed configuration. And sometimes it's easier to do calculations in the undeformed configuration. The physical meaning of that stress, Euler-Kirchhoff stress, the second Euler-Kirchhoff stress, is not always very clear, but it is convenient because it's symmetric. So there's an advantage of using a second Euler-Kirchhoff stress is that it's energetically conjugate to the green Lagrange strain. Secondly, it is parameterized by material coordinates only, and you can see that derivatives are all taken with respect to the undeformed configuration X. And in addition to that, the Euler-Kirchhoff stress, the second Euler-Kirchhoff stress can be interpreted as taking the force vector in the current configuration and locating that corresponding vector in the undeformed configuration. And so this stress tensor, it is kind of a fictitious force divided by the corresponding area in the reference configuration, but it does have value in the sense that it's symmetric and it's energetically conjugate to this value. So it is very simple to calculate as well. If I know the F, I can just do this calculation straightforwardly. So with that said, we'll continue then with the constitutive relationships. So let's start with that. So today's lecture is really about constitutive law, and that long introduction was to demonstrate for you that the stresses are related to strains and that we should consider a way to figure that out. So if I went to the lab and I have spring and I have a mass M, and that mass is going to cause this spring to stretch an amount, you can measure the weight and measure the deflection in the labs, and that's going to give you a stiffness. It turns out that this stiffness provides resistance to deformation, and we know that if you change the mass and you change the mass many different ways, that the deflection will change. And so Hooks in 1678 looked at the idea of testing multiple rods with different thickness, different diameters. So many different cross-sectional areas. And when that was done, it was found that for the same material, if I measure the deflection, P, and I have the load P is applied, so the load is P is applied, and I'm measuring the deflection here at the end, that deflection will depend upon the cross-sectional area. So if this cross-sectional area was A1, A2, then this deflection was also changing. It was also found that if the length of this rod was changed, that deflection also changes. So you will get different final lengths, L1, L2, different lengths. So you get different stiffnesses. What was found then is that if I were to then normalize somehow, so if I'm able to take P and divide that by area for the same rod and for different rods, but the same material, then I took the change in length delta, which is final length minus initial length divided by initial length, and I tested multiple rods with different cross-sectional areas with multiple lengths, that all the lines landed in one place with a common stiffness, with a common slope, which they call modulus. And obviously this is stress per our course, this is strain. And so that's when we were able to discover that there is a consistent set of parameters that describe the material, and that stress must be equal to C, a constant C times epsilon, and C later on was called the Young modulus. E. And so stress in one-dimensional theory, sigma equals E times epsilon. The issue that we have in place is that we do have 6 components of stress, 6 components of strain, so we have to figure out a way of relating one to the other. So let's look at a class of materials, and we're going to tackle now a class of materials that do not depend on the strain history. So a class of materials that do not depend on the strain history. And so to tackle that, we're going to say that in these cases, the body behaves elastically. So in other words, I apply loading to the structure, and when I do that and I remove the loading from the structure, the body returns back to the original state. It's fully reversible, so it's fully elastic. In other words, if I had a little bar and I apply a load P, it will deform like this, that much, say. But now I remove the load, this is undeformed, deformed, and now I remove the load, and it goes back to the original state. So remove the load, and it goes back to the original state. We call this an elastic, reversible, elastic material, meaning is reversible, okay? And so let's define the existence of a strain energy function. Define the existence of a strain energy function. And so if I define the existence of a strain energy function, W then becomes the derivative of, then if the strain energy function does exist, then we can say that stress equals dW epsilon, d epsilon. And so when I look at that, I get this is stress strain curve, say. So I know that stress is related to the strain because we showed that they must be related through this relationship. We also showed that the virtual work done by the external loads happens to relate stress to strain in some way, and that the stress and the strain are married in this way. And so as a consequence, you may have a relationship of stress and strain. We showed it for what Hooke showed, which was basically, we showed it for Hooke's law. We showed it here in this relationship here, stress versus strain. And now I'm looking at a more general form. So this is, maybe the stress strain looks like that. And this is strain at point 1, strain at point 2. So we invoke that independence, path independence. In other words, if I load the structure, then it will unload back in the same way. So there's no plastic deformation there. It's fully reversible, and there's no hysteresis. So in other words, if I were to integrate the area under this curve, I get the integral from epsilon 1 to epsilon 2, sigma epsilon d epsilon, and that's equal to epsilon 1, epsilon 2. But sigma epsilon here has been, we defined the strain energy functional to be this. So then I have dw epsilon, d epsilon, and this is times d epsilon. And so, in other words, this is basically w epsilon 2 minus w epsilon 1, because you can integrate this by parts to get that. And notice how the work done is only a function of the difference in the strain energy between two states, this point and this point. And so in a closed loop, the work done over the path is 0. So if I were to find the work done by going up and then going down, the work done is 0. So this means that the material is irreversible, implies that there's path independence. And so in 3D theory, I can further expand this and say, well, in 3D theory, I have 6 components of stress. And so the strain energy functional is going to have to be a function of epsilon 1, 1, epsilon 2, 2, epsilon 3, 3, epsilon 1, 2, epsilon 1, 3, epsilon 2, 3, respect to epsilon ij. So I must have a way of relating sigma ij to the strains through this functional relationship. And that is going to allow us to then move forward. Now, notice how this is a second order tensor. That's a second order tensor. In this case, if a strain energy functional exists, then the material, if the strain energy functional exists, then what we're saying is that the material is elastic. In other words, I apply a load, and when I remove it, it returns to the original state. And how do you find this relationship? How we determine the relationship between stress and strain? We determine that using the idea of material characterization. That's how we will do that. So for the one-dimensional case, which is this one right here, let's look at what W will look like. And we know for linear materials, stress equals C epsilon. We show that through Hooke's law, or E times epsilon. But we're going to use C times epsilon for generality for now. And so the strain energy function on W must be 1/2 C epsilon squared. So when you take the derivative of W with respect to strain, you get twice times 1/2 C epsilon, which is C epsilon. That's exactly stress. So this works, and the energy functional for a one-dimensional problem will look like that. Very similarly, we can then generalize and see what it will look like for 3 dimensions. And for 3 dimensions, you know, in 1 dimension, clearly the slope E or C is the derivative of sigma respect to epsilon. And you can see here that the derivative of sigma respect to epsilon works because sigma is C times epsilon. And here clearly that's just C. So this relationship works for 1D. So if I have a linear elastic material, then for a linear elastic material, I must have something equals the derivative of sigma ij respect to, and let's use Sij for stress, partial of Ek. We can use KL. Sorry about that. And so therefore, if the slope for 1D is this one, then the slope for 3D is this one. And so therefore I must have, since Ij, K, and L are 4 indices, I must have a 4th order tensor that looks like this. In other words, I have 81 indices, 81 components of the 4th order tensor. These are 4th order tensor. Notice how this is also equal to, and I can look at this carefully here, Sij, I already said that Sij is this expression right here. So that's the derivative of W respect to epsilon Eij. So I'm going to use the epsilon I just for small deformation. I can use E for green Lagrange, which is for finite deformation. And so what I get is this expression. So I have a 4th order tensor, 81 components that give me this slope here. Okay, so very interesting idea. And as a consequence, what we're really saying is that this tensor C can be written asCijkl, and a 4th order tensor in this case becomes the outer product with a basis given as this. We normally have not been writing it, but these are your unit vectors that define the basis. And so theseCijk's are components of this 4th order tensor. That's a 4th order tensor. And so there's 81 components here. The other point I want to make is that when we consider, and in this case, we're considering linear material. And in this case, we're also talking about a conservative mechanical deformation process, because the deformation disappears on the removal of these loads. And so furthermore, we also know that there must be 81 components of C, And we know that because we've examined here, I, J, and KL can take values of 1 through 1 through 3. And there's 4 components of those. So 3 to the 4th power gives us 81. So furthermore, we can define then the fact that sigma or stress Ij equalsCijkl EKL. And you can check that when I take the derivative of Sij respect to EMN, that in fact I will get Cijmn. I'll get that, which is what I've shown already here. So this relationship holds for linear elastic material. There's 81 components here. And because the strain tensor is symmetric, then Sji is also equal to Sij, which is also equal toCijkl, EKL. And by swapping I and J, because I and J are symmetric, then I have Cijkl, EKL. In other words, Cijkl equals Cijkl. And so that by itself brings me down to 54 independent components from 81. And then I can do another one, which is that EKL is equal to ELK. So that gives me another way of further simplifying everything. So I can say then Sij equals Cijkl ELK, because I can do that. So I can swap K, L, and K. And when I compare this to that, clearly, if this is equal, then the coefficient is also equal. So Cijkl equals Cijlk. And that now brings me down to 36 components, independent components from 81, because many of them are the same and equal. And that has to happen through, it has to happen. That has to be the case. And so now, because I have a conservative deformation process, and I can further reduce everything more, and that's because I can take this derivative 2 ways. I can take it taking this first and then this next, or this first or taking that next. And so all that does then, it brings it now saying that Cijkl must be equal to CKLIJ, because it doesn't matter how I take the derivative. I can do it this way or this way, and I should get the same answer. And that's because I have a conservative deformation process. So I can have this situation or the second way, which is KLIJ. And now that further reduces it from 81 components to 54 to 36 to now 21 independent constants, which can be measured in the labs. So now, because of that, we have now really simplified the constitutive relationship quite a bit. And now I can say, okay, sigma ij equals Cijkl epsilon KL, or E, let's use big S for large deformation E, which corresponds to the Pula-Kirchhoff stress. But in general, this is what I get. And so here now, instead of 81 components, I have 21 components of they're independent. So very important idea there that I think is worth thinking about. And so now, when I think further about this, how to write this out, is very simple. I have sigma 1, sigma 2, sigma 3, sigma 2, sigma 1, and sigma 1, 2. And now I have C11, and then here I'm going to have a 6x6 that's symmetric, 36 components, but 21 independent because it's symmetric. So I'm basically independent. And you can see here that since this is symmetric, right? So under is expanding here. And you'll get that, you'll actually get that this is twice when you do it. And you get C1111, C1122, C1133, and so forth. So I'll invite you to expand. There should be 6 equations here. I invite you to expand this. There's 6 equations here. Expand it out and then write it in matrix format to fill the rest out. And you'll get a 6 by 6 here when you do that. Some of the components will add up and you'll get 2 of them. Remember that these are the off-diagonal terms that cause stretching of the volume cube. And then this one causes shearing or the angle change. And so here we have defined now the constitutive law for the most general formulation, which is 21 independent constants. These are fully anisotropic material. And we really not have made any assumptions. We have not made any assumptions other than the fact that it's a linear material and that is fully reversible as well. So very good. We've made great progress there, and we're able to understand what is going on with the most general form for a linear elastic material. Now let's consider now the idea that I may have an isotropic material. So isotropic material. And for the isotropic material, I want to really define what that means. It just means that if I were to have a block and I cut samples, I will cut it this way randomly. Doesn't matter which way I cut rods out of this cube. If I were to test it, then if I test this material, I'll get the same properties, doesn't matter what direction. So a material is said to be isotropic if its properties do not depend upon certain preferential directions. In other words, the elastic tensor, this CIJKL, for an isotropic material becomes invariant with respect to any coordinate transformation. And so there is a way to ensure that that happens, and that only happens if the strain energy function depends on the invariance of the strain tensor. So that will push you to have a constitutive model that's fully invariant. In other words, if I have a strain energy function of W, that W depends only on E bold. So all the components of E, which is, there's 6 of them, equals to W, and then it's going to be a function of the first invariant of E, second invariant of E, and third invariant of E. These are the most general cases. This is not even linear elastic at this point. This for isotropic material in the most general sense, and you will see this a lot in analyses of hyperelastic materials. And what I can do now, I can define what these functions are. And I will do that now. So we covered that already, but I think it's worth going through that again. So the first invariant was covered, was this one, which is the trace of E. And that's just adding up the diagonal terms of the strain tensor. The second invariant is this one. It's a trace of E squared, and that's just simply EI J JI. And we did this before, so it's not a problem. We're just trying to show you what we have. And then we have the third invariant of E. And that third invariant is EIJ, EJK, EKI. Okay? And so if I wanted to now calculate the stress based on this strain energy functional, right? So if I want to calculate that, then I'll simply get Sij equals the derivative of W with respect to Eij. And we can use different variables since I used Ij earlier. Let's use M and N. And now I have to take the derivative of W with respect to F1 respect to EMN plus derivative of W with respect to F2 derivative of F2 respect to EMN plus derivative of W respect to F3 derivative of F3 respect to EMN. That's what I get. And so we can now very quickly, and what I do is chain rule there because W depends on F1, F2, and F3, but F1, F2, and F3 depend on these E's. So I'm just trying to quickly work through that. And for me to get the stress out of this most general term form for an isotropic material, but this could be nonlinear. It's just that this can be a nonlinear behavior, but for the material to be isotropic, it does need to depend on these invariants so that it doesn't matter which way you look at the constitutive law. If you extract blocks of material out of a bigger block, it doesn't matter in which direction you test it, you can get the same answer. The same characterization, doesn't matter what. But this is the most general term. It's not even linear. This works for nonlinear hyperelastic materials. As long as it's dependent on these three strain invariants, then that's what we get. And so if I can find now these derivatives here fairly quickly. So let's walk it through. Derivative F1 respect to EMN, but this is the derivative of EII EMN, because I'm looking at this one right here, the first invariant. And so that's going to be equal to Kronecker delta, del IM, del IN. I cancel out, you get del MN. So I just get that expression. If I look at the second invariant now, with respect to EMN, then I get the derivative of EIJ respect to EMN, EJI plus the derivative. Well, then I have EIJ as the derivative of EJI respect to EMN. And then here, that's a Kronecker delta again, del IM, del JN. And this is Kronecker delta again, del JM, del IN. And so here, I and J cancel out from these ones. You can work it through. And what you get at the end is twice EMN when you work it through. So yeah, it collapses to get 2 EMN. And now I have the derivative of the third invariant, which now is a little bit longer, but is nothing to be fearful of. Derivative of EIJ respect to derivative of EMN times now EJK EKI plus the derivative of EI. And then now I have the first term plus EIJ EJK derivative of EKI respect to EMN. Here, that's Kronecker delta again, delta IM, delta JN, that's Kronecker delta del JN, del KN, Kronecker delta del KN, del IN. And now you can collapse again this J and I cancel out. You can bring it over there and so forth. And when you do that, you will get 3 ENK EKM. Okay, so those are you get these three quantities, and notice how the stress now depends on this. So basically, let me write it out down here, the summary of that. So SMN is equal to derivative of del with respect to F1, and then del MN plus derivative of del with respect to F2 times twice EMN plus the derivative of del with respect to F3 times 3 times ENK EKM. You can see how SMN is a quadratic function, up to quadratic function. For the material to be isotropic, this is what we get. And so what if now I want to consider linear elastic material? If I want to consider linear elastic material, then we should then figure out how to get there. So what I want you to notice is that if I want to look at a linear elastic material, isotropic material, I want to more closely look at what I have here. So let's look at, this is for the most general case. You can see that if I want a linear elastic material, clearly this is a function of this quadratically. So for linear elastic material, I don't want this term to show up. So I don't want W to depend on F3. So I don't want W to depend on F3, because otherwise then SMN becomes a quadratic function of that. I want SMN to be linearly dependent on EMN, but you can see here that there's this function here. So I need a constant there. I don't want W to depend on F2. I want W to depend on F2 in such a manner that I get a constant when I take this derivative, so that SMN is linearly dependent on EMN. Here, respect to this one here, this one should not be just dependent on del MN, because that will not work out. It's just a constant. I need this to be linearly dependent on EMN somehow. So this should be a quadratic function. So F1, W should depend on a quadratic function F1. So when I take that derivative, I'm able to get something to do with EMN. So I need a linear elastic material. And so that's what I want to come up with. So W does not depend on F3, clearly. Otherwise, then S and men becomes quadratic constraint, and that's not linear. And then somehow S has to be linear, W has to be linear with F2, because I need, when I take that derivative, so W to F3 is 0. I want this W with respect to F2 to give me a constant of some kind. And I need that because it's already dependent linearly on EMN. So I don't want to have something here with EMN, otherwise it would be not very good. Here, now though, F1, if you remember what F1 is, F1 was the trace. So somehow I need this SMN to depend linearly on that. So therefore, W should be a function of F1 quadratically. So when I take the derivative, I get a linear function, which then will work out to be linear. So W has to be quadratic with F3, F1. So WF1 be proportional to to the strains somehow. And it has to be because this is a constant, del mn. So I need something to show up here that has E. Okay, so we need that for sure. I'm cleaning this up for posterity. And so therefore, I'm going to say that for linear elastic isotropic material, W equals, these are the components of strain. I could have written it like this. I want this to be equal to a constant A1, F1 squared plus A2, F2. As I said, it was linear with F2, quadratic with F1. But it should not depend on F3 because we already showed you that I don't want S to have F3, otherwise I'll have it will not be linear. And so I can now quickly take this derivative, right? So we have to take these derivatives here. This one's right here. So let's take the derivative S. I'm gonna go back again. I'm gonna repeat what I wrote here. Smn equals derivative W respect to F1 del Mn plus the derivative W respect to F2. And then now that's twice EMN. And when I now take that derivative, I get twice A1 F1, but I know what F1 is. F1 is the trace of E, and then plus the W respect to F2, which just gives me A2. So A2 times the twice I have here, EMN. So I came up with a way of relating SMN to the strength, and you can see is linear. And we came up with the most general linear elastic constitutive relationship. Now, this 2A1 is typically called lambda. And this coefficient here is called mu. And those are called the Lamé parameters, and it's actually called the Hooke's law. It's referred as Hooke's law. So SMN is actually equal to lambda EII plus twice mu EMN. And this is the most general form of a linear isotropic material. And lambda mu can be determined through testing. So there's only two independent constants that we need to be worried about. And you can calculate what CIJKL looks like by taking the derivative of SMN respect to EMN. We won't do that here, but that derivative can be calculated. Now, the next thing I want to do is to invert. I want to invert this relationship for E, because I want to show you some cool things that come up later. I want to show you that we did this mathematically, but physically, I can get the same answer as this without having to go through all this math. I can show you that this works out mathematically. But the first thing I want to do to be able to get there is to find the trace. And so the way you want to do this is to find the trace of both sides of the equation. So I can invert it for this. So I'll continue here. And when people have done testing, what they have found is that lambda that I'm showing here is equal to E nu 1 plus nu times 1 minus nu, 1 minus 2 nu, and that mu equals E over twice 1 plus nu. So that's what that is. And this is basically the shear modulus. There's a shear modulus here. nu is a Poisson ratio, and E is the modulus. And when you invert, if I want to invert this relationship, it's very easy. You simply write this in matrix format and then invert the matrix. And the inverse of this relationship, when you do it, is going to find epsilon ij to be equal to minus nu over E sigma kk epsilon or del ij plus 1 plus nu divided by E sigma ij. That's what you get when you do that. Now, I did this through very rigorous mathematics. You can see that here, but I can get to the same answer doing physical experiments. I can get to the same answer using physical experiments. So let's conduct some physical experiments. What I'm going to do is I'm going to apply a load and a load here and a load there, and apply sigma 1, 1. And I want to measure the strain going this way and the strain going that way. And I'll find that the strain is going to be epsilon 1, 1 equals the modulus, sigma 1, 1 divided by the modulus. But if I look and say this is the one direction, and that's a 2 direction, and that's a 3 direction, then I'll find that epsilon 2, 2 is going to be the Poisson ratio times epsilon 1, 1. Because that's the differential Poisson ratio. So I get negative sigma 1, 1 over E. And epsilon 3, 3 likewise would be negative sigma 2, 2. And this should be sigma 1, 1 over E as well. So that's the first experiment. I can now conduct a second experiment where I apply the loads, but now I apply them in the 2 direction. So instead of applying loads in the 1 direction, I'll apply loads in that 2nd direction. When I do that, I'll get epsilon 2, 2 equals sigma 2, 2 divided by E, but epsilon 1, 1 would be equal to the negative, and now I have sigma 2, 2 divided by E, and epsilon 3, 3 will be the negative of sigma 3, 2, 2 divided by E. And I can then go ahead and continue. So this is loading in 1 direction. This is load in 2nd direction. And I get epsilon 3, 3 now to be sigma 3, 3 divided by E. And now the other directions, I get the Poisson ratio effects. I can now apply the principle of superposition. And when I do that, when I apply the principle of superposition, what I'll get is that I can add the strains due to the load in the 1, 2, and 3 directions. So I get epsilon, when I add this one, and that one, for example, for epsilon 1, 1, I get to be, I'll get sigma 1, 1, so I can factor 1 over E, first of all. And I get the minus nu times sigma 2, 2 plus sigma 3, 3. And then I will get epsilon 2, 2 equals 1 over E sigma 2, 2 minus nu sigma 1, 1 plus sigma 3, 3. And epsilon 3, 3 equals 1 over E sigma 3, 3 minus nu sigma 1, 1 plus sigma 2, 2. And that's very exciting because we derive this first term, and that term right there was derived using a completely different method, mathematical method. This is all mathematical. This derivation here was fully mathematical. Yet, using physics here, which started about here, physical experiments, virtual physical experiments, we got the same answer for those strains. So when you expand these, that's what you will get. And furthermore, you will say where this term showed up. Well, that's when I apply shear is actually even simpler. Shear loading will result in simply, for isotropic materials, will simply result in epsilon 1, 2 twice equals G sigma 1, 2 divided by G, the modulus, the shear modulus, and then twice epsilon 1, 3 equals sigma 1, 3 divided by G, and twice epsilon 2, 3 equals G2, 3 divided by G. And this term shows up in that manner. While this term will be 0, because anytime if I have epsilon 1, 2, this term goes away because of Kronecker delta, this stays, and so I'll get exactly the relationship of shear strain to shear stress. So that's very good. When I go to a 3D orthotropic material where I can also apply a superposition principle, and if the material directions, the different material directions were different, not isotropic. So meaning if I had a material and the loading this way was different from the loading, the material was different this way, the modulus, and it was different in the thickness direction. So if I were to have that situation, and E11 was different from E22, was different from E33, then I can apply the same superposition I did, and assuming the Poisson ratios would be different in every direction, and the shear modulus would be different in every direction, I can apply the same superposition principle. Watch the video below. I have a YouTube that goes into that. But I derive this relationship without using any math, just virtual experiments. So, I mean, for the isotropic case, this is just nu, E, 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 nu, E, E, and that'll give you exactly what I've shown you in the previous chart for the isotropic case. And that'll match exactly what we had in the previous slide. Here I define gammas to be twice epsilon 2, 3, and so forth. So very good there. I can invert this relationship and get a more complicated stress-strain relationship. When it's an orthotropic material, it's quite complicated. When it's a isotropic material, you get exactly what I showed you in the previous slide, but I wrote an index notation. If I invert this relationship, now I get exactly what I had just showing you in this slide right here for orthotropic. It just simplifies to this very nice, relationship. And so, yeah, so with thermal effects, you can have thermal effects. We won't be going to that deep here. I also want to point out, that's called a shear modulus. You also have a simple tension case. For simple tension case, you can see how this is a strain that you get due to a simple tension case. And that's what we used for our experiments earlier. Pure shear, when you have pure shear, only tau and tau show up here, and the strain then just becomes these quantities here. Because those are the only components that matter. When I have a hydrostatic compression where these components, I'm applying loading in this direction, this pressure, I'm compressing that cube, the strain then becomes this relationship. And when you add the trace of that, this trace is actually changing volume. And so you can actually calculate the bulk modulus using that information. And the bulk modulus is the inverse of the trace, as you can see here. So the higher, the closer the Poisson ratio is to 0.5, this denominator blows up. And so you will have very little change in volume because this trace here, if V was, the Poisson ratio was close to 0.5, this symbol here, the trace, becomes close to 0. So the bulk, no volume change basically, and then the bulk modulus becomes close to infinity. You can also look at the relationships of the different parameters. Just pause the video here and look at the relationships that exist, but this bulk modulus, this Poisson ratio, so all these are known. You guys are familiar with this, but just showing you how they can relate to each other. This is the shear modulus G that I was using earlier, and this is one of the lambda constants I discussed earlier over here. So all these relationships have been covered. Another point I want to make, an isotropic tensor can be written in this manner. You can write it this way. And then you can show that this isotropic tensor is invariant to any transformation. So very easy to show and to develop. And you can do a transformation to that equation by simply doing an arbitrary transformation. By substituting this into this equation here, you can then work it all out. And when you do, you will find the C prime equals C. So I invite you to pause the video, do it yourself at this point in time. Continuing on with constitutive law, I want to bring to your attention that the strain energy functional is going to become important sometimes, and we'll be looking into that. The strain energy density may need to be calculated for some situations. And to calculate strain energy density, all you have to do is look at the area under the stress strain curve. And that's going to entail taking the integral of sigma ij d epsilon ij. So that's the strain energy density. This is going to come up a few times, so it's very important to understand that that's the area under this curve. And for a linear elastic material, we can determine what that is by simply calculating U equals 1/2 Cijkl epsilon ik epsilon, or epsilon ij, should I say, x epsilon kl. And you may ask me why that's the case. Well, if I look at the one-dimensional case for linear elastic, so this is for any curve, and this is for linear elastic. And so for linear elastic, the area under this curve is strain equals 1/2 sigma epsilon, but that's for 1D, but sigma C epsilon times epsilon, that's 1/2 C epsilon squared. Analogously, for 3D, you're gonna have 1/2 sigma ij epsilon ij, but I know that sigma ij is this. Sorry, sigma ij is this times this. So that's why we get the expression you see here. And you can simply substitute this expression to get the strain energy density for a linear elastic material. So with that said, today concludes this particular lecture. We'll pick it up with a new topic to try to summarize the equations that we have.